Hello and welcome to Controllers Tech. In this video, which is part of the Mongoose networking library series, we will learn how to integrate the Mongoose library with the W5500 SPI to Ethernet module. By using the W5500, we can bring the powerful features of the Mongoose library to low-end microcontrollers such as the STM32F4 as well as other F4 and F1 series MCUs. I have already covered a separate series on the W5500 module, but you do not need to watch that series to follow this tutorial. The Mongoose library already includes built-in support for the W5500, so all we need to do is connect it to the SPI driver of the microcontroller. We will go through this entire process step by step and see how everything works in detail in this video. Before we start working on the project itself, let us first take a quick look at the main features of the Mongoose networking library. Mongoose is a TCP/IP network stack that comes with an embedded web server, an MQTT client, built-in TLS support, and firmware update functionality. It is widely used by hundreds of companies, both small and large, ranging from individual developers to multinational companies such as Bosch, Siemens, Google, and Samsung. NASA also uses Mongoose on the International Space Station, which clearly shows how reliable and powerful this library is, and why you should consider using it as well. With Mongoose, you can quickly create professional-looking web-based device dashboards without having any prior knowledge of web development, and you can also connect your device to cloud platforms like AWS IoT or to your own private server. For this project, I am going to use the STM32F4 46RE microcontroller. Since this board does not come with a built-in Ethernet adapter, Mongoose does not officially support it out of the box at the moment. Because of this, we will first create the project using STM32Cube.MX, and then we will manually include the Mongoose library into the project later. Now, open the Mongoose documentation, go to the Tutorials section, and then open the Device Dashboard tutorial. In this tutorial, they have explained the general process of implementing the Mongoose library on any development board. The first step in that process is creating a skeleton firmware, which is basically a minimal working firmware that includes basic functionality such as printf support. However, the process described in the documentation is meant for development boards that already have an Ethernet peripheral. Since that is not the case for our board, we will skip this part and instead create the required setup ourselves. Open STM32Cube.MX and create a new project. For this project, I am using the STM32F4 46RE microcontroller. Let us begin with the clock configuration first. The clock source is provided by the SD-Link, so we will bypass the external crystal. Although the board has an 8 MHz crystal on it, we will configure the system to run at the maximum frequency of 180 MHz. Next, we need to enable the SPI interface for connecting the W5500 module. Make sure the SPI is enabled in full duplex mode for proper data communication. The SPI MOSI, MISO, and clock pins are already configured automatically, so now we need to configure the chip select and reset pins manually. I am going to use PD6 for the chip select pin and PC7 for the reset pin. Configure both of these pins as output pins and give them proper names for better readability. Ensure that the SPI data size is set to 8 bits and that the first bit is transmitted as MSB first. Also, configure the SPI prescaler so that the baud rate stays around 10 megabits per second. That is all the configuration needed for the SPI interface, so now let us move on to the UART configuration. I am going to use UART2, because it can be used as the virtual COM port on the Nucleo F446 board. I also plan to display an ADC value on the web UI, so I am enabling ADC1 and selecting channel 0. The ADC resolution is 12 bits by default, which is sufficient for our use, so we will keep it unchanged. There will be two LEDs controlled from the web UI as well. For this, let us configure two GPIO pins as output pins where the LEDs will be connected. That completes all the required peripheral configuration, so now let us generate the project. Give the project a suitable name and make sure the selected IDE is STM32Cube IDE. Choose the project folder and click on Generate Code to create the project files. Once the project is generated, import it into STM32Cube IDE. This is the main file of our project, where we will add the required code. Now, go back to the Mongoose documentation to implement the additional steps needed for the skeleton firmware. We do not need to enable the Ethernet IRQ because we are not using the built-in Ethernet drivers. Copy the provided printf statement from the documentation and paste it inside the infinite while loop. Next, copy the custom write function that redirects printf output to the UART. Make sure to select and configure the same UART instance that you enabled earlier in CubeMX. After that, copy the mgmillis function and paste it into the main file as well. Now, when we run the project, we should see timer ticks printed on the serial console. Let us build the project once to check for any errors. It looks like there is an issue related to the printf statement. To fix this, we need to include the cyan.io header file in the main file. Alright, the project builds successfully now, so let us flash it to the board. Open the serial console to observe the output logs. Here, you can see that the ticks are being printed every 500 milliseconds. This confirms that our skeleton project is working correctly and is now ready for the next steps. The next step is to implement the Mongoose library. However, instead of doing this manually from our existing project, we will use the Mongoose wizard to simplify the process. Open the Mongoose wizard, and create a new project. Select the option to create a new C++ project. Now, choose a folder where you want to store the generated project files. After that, we need to select the target architecture for this project. Mongoose does support STM32 boards, but only the ones that come with an Ethernet PHY by default. At the moment, it does not directly support W5500 integration for STM32 devices. Because of this limitation, we will select the next easiest supported option, which is any Arduino board using the W5500 module. Later, we will port this project so that it works with our STM32 setup. The build environment is automatically selected as the Arduino IDE. This is why we already created a project in STM32Cube IDE earlier, so that we can later copy the required files into it. Next, choose a simple LED dashboard to get started with the web UI. The default dashboard is now ready, and we will start adding the required elements to it. The container with two LEDs is already present, which is perfect because we have also connected two LEDs to the STM32. Now, let us copy this container so that we can add a gauge element inside it. Delete the toggle buttons from the copied container and rename this container as ADC data. After that, add a gauge element inside this container. This gauge will be used to display the ADC values, which we will map from a range of 0 to 100. Let us also add ticks to the gauge, with a gap of 20 between each tick. Now, we need to add the REST API endpoints. These endpoints will be used by the MCU to control and update the web UI elements. The LED endpoint is already added by default, and it includes two Boolean attributes to control both LEDs. Let us add one more endpoint specifically for the ADC data. Create an integer type attribute for this new endpoint. Since the ADC data will range from 0 to 100, using an integer attribute is appropriate here. Mark this attribute as read-only because this value will only be sent from the MCU to the dashboard. It will not receive any data back from the web UI. Now, go back to the page content and select the API variable as ADC data. Then open the Settings tab and make sure that WebSocket is enabled, as the web UI elements will be updated using it. That is all the configuration we need at this stage. Finally, click on Generate Code to generate the project files. Open the project folder, and here you can see the files generated by the Mongoose wizard. Although these files are created for the Arduino environment, we will port them so they can work with STM32. Now open STM32Cube IDE, browse to the drivers folder, and create a new folder named Mongoose. Copy all the generated files from the wizard and paste them into the Mongoose folder that we just created. Next, we need to modify the mongoose config.h file, so open this file. First, replace arduino.h with main.h, so that all the required STM32 headers are included automatically. You can notice that the architecture is set to custom, and the W5500 driver is already enabled. If you want to use a static IP address, you can simply remove the comments and set the IP values manually. I am going to use DHCP, so I will leave these options disabled for now. Let us build the project once to see the current status. You will see around 474 errors, but do not worry, as we do not need to fix them one by one. We first need to add a few standard header files such as standard library, standard boolean, and string header files. After adding these includes, build the project again. Now, we are left with only 3 errors. These remaining errors are related to the integration of Mongoose time handling with Arduino's time library. If you check the Mongoose documentation, you will see that we need to enable custom millis for timekeeping. We have already defined the mg-millis function earlier, so now we just need to enable custom millis in the configuration file. Build the project again, and this time you should see 0 errors. At this point, we have successfully integrated the Mongoose library with STM32. The next step is to implement the SPI driver, so that Mongoose can communicate with the W5500 module. Inside the configuration file, you will find an SPI structure that contains the functions used by the library to talk to the W5500. These functions include begin, end, and transaction. These functions are declared as external functions, which means we must define them somewhere in our project. If you open the Arduino project generated earlier, you can see how these functions are implemented for Arduino. Let us copy those functions into our Cube IDE project so we can modify them for STM32. We will start with the SPI begin function. Since the SPI peripheral is already initialized, we only need to reset the CS pin to low here. Similarly, in the SPI end function, we simply set the CS pin back to high. Next comes the SPI transaction function. In Arduino, this function performs an SPI transaction and returns the received byte. We will implement the same logic using the STM32 HAL library. Call HAL SPI transmit receive to transmit and receive 1 byte of data from the device. The received data is stored in the rbyte variable, which will then be returned by the function. With this, the SPI driver integration with the Mongoose library is complete. Now we will test the basic working of the library. Start by including the mongoose glue.h file in the project. You will see an error because the Mongoose folder is not yet added to the include path. Go to the project properties, then CC++ build settings, and open the compiler include path options. Add a new include path and select the Mongoose folder that we created earlier. Save the settings and build the project again. The include error should now be resolved. Inside the main function, add the reset sequence for the W5500 module. This reset sequence involves toggling the reset pin with a small delay in between. After that, initialize the Mongoose library and call Mongoose poll inside the while loop. Now build the project and flash it to the board. Open the serial monitor to view the output logs. As you can see in the logs, the W5500 driver has been initialized successfully. The HTTPS listener has started, and the Mongoose library is now running. We have also received an IP address using DHCP. Copy this IP address and paste it into a web browser. You can now see that the Web UI dashboard has loaded correctly. At this stage, the REST API endpoints are not yet connected to the MCU, so the UI elements will not respond. Even so, this confirms that our basic Mongoose setup is working properly. Before moving forward, let us first take a look at the hardware connections. The image on the screen shows the complete wiring used for this project. The W5500 Ethernet module is connected using the SPI1 interface, and it is powered with 3.3 volts directly from the Nucleo board. A potentiometer is connected to pin PA0, and two LEDs are connected to pins PA1 and PA4. Next, open the Mongoose glue.c file. This file contains the REST API functions that need to be modified so that the MCU can communicate with the Web UI. We could modify these functions directly in this file, but they will be overwritten if we regenerate the project using the wizard. Therefore, it is a better approach to define these functions again in the main file and slightly rename them to avoid multiple definition errors. The set LEDs function will be called whenever we change the state of the toggle buttons on the Web UI. Inside this function, we will simply set or reset the corresponding LED based on the state of the toggle button. In the same way, the get LEDs function will be used to fetch the current LED state. Here, we will read the GPIO pin state and pass this information to the corresponding elements in the data structure. Next, we need to write the function that provides the ADC data. This function will read the ADC value so that the gauge on the Web UI can be updated. Inside this function, we will simply pass the value returned from the read ADC function. Now, let us define this read ADC function. In this function, we will read the ADC1 using blocking mode for simplicity. Since the ADC resolution is 12 bits, we will use a map function to convert the 12-bit value into a range from 0 to 100. This converted value will then be returned and passed to the ADC data endpoint. In this way, the gauge will display values from 0 to 100 for the full 12-bit ADC input range. Now, the custom getter and setter functions that we defined will not be recognized by the Web UI automatically. Because of this, we need to register these functions manually. You can find the required details for this step in the Mongoose documentation itself. Inside the Mongoose wizard, open the section related to WebSocket updates. Here, you will find the function used to register a custom HTTP handler. We will add this function inside the main function, but only after initializing the Mongoose library. The first parameter of this function is the API endpoint name, which in our case is LEDs. The next parameter is the getter function, which reads data from the MCU, and the last parameter is the setter function, which sends data to the MCU. In the same way, we will register the getter function for add data. Since this endpoint does not require a setter function, the last parameter will be set to null. Next, we also need to implement the Mongoose WebSocket reporter function so that data can be sent to the Web UI periodically. I am configuring the WebSocket to transmit the ADC data every 100 milliseconds. That is all the programming required for this step. Now let us build the project and flash it to the board once again. The same IP address has been assigned again, so let us simply refresh the web page. Now, let us test the LED controls first. You can see that the LEDs are responding correctly to the toggle buttons on the web UI. This confirms that the LED control functionality is working as expected. Since the LEDs are working fine, we will now test the ADC data using the potentiometer. As you rotate the potentiometer, you can see that the gauge value updates in real time. The 12-bit ADC values are being mapped to a range of 0 to 100, and these values are then sent to the gauge. The gauge is displaying the data accurately based on the potentiometer position. Both elements on the web UI are functioning properly without any issues. This confirms that we are successfully running the Mongoose library on the Nucleo F446 using the W5500 module. This brings us to the end of the video. I hope this tutorial helped you understand how to integrate the Mongoose networking library with the W5500 module, allowing it to be used with any STM32 MCU. You can download the complete project from the link provided in the video description. If you have any questions or doubts, feel free to leave them in the comments section. Keep watching, and have a nice day ahead.